You. Welcome back to yet another lecture of Stat 568 Design and Analysis of Experiments. This will be the final lecture of Chapter 2 on multi-factor designs, but don't worry, because after a quick interlude on multiple testing, we will be back with even more factors to discuss in our experimental designs. This lecture, we'll be looking first at nested factors, because sometimes you have one factor and it happens to be nested within another factor, and we have to figure out how to analyze that correctly. And we'll also look at ANCOVA, or the analysis of, covariates. It's ANOVA with covariates, because sometimes you have extra measurements that you can use to help describe the responses in your models. And we'll be talking about how to analyze that data today, as well as type 1, type 2, and type 3 ANOVA. It's terrible notation, or terminology, I should say. But we'll get into that so you can learn all about it. So let's go see what that's all about. And welcome back to yet another lecture of Stat 568 Design and Analysis of Experiments. This is our 7th video lecture of the series, and we'll be finishing Chapter 2 of my online lecture notes. This will be a bit of a grab bag lecture, kind of tying up all the loose ends before we move into Chapter 3, which will be on multiple testing, a complete new topic to discuss outside of what we've done so far. But what I did want to talk about today are a few different topics, including nested factors, ANCOVA, which is in my course notes as the final section, and type 2 and type 3 ANOVA. So I think the best thing to start with is nested factors, because this is something that we discussed a little bit when we did the split plot in the previous lecture, but now things are, there's many different ways to have nesting in statistical models, so it's good to consider that. We are going to talk about nested factors. So the last time we did the split plot. And in the split plot, we have, let's say, 2 factors. Again, it could be more than 2, but just for simplicity, we have, say, 2 factors. And one of them is, randomized within another one, right? And we'll say 1 randomized inside of another. The examples, or the reason we would do that, is because one factor is hard to change. The other factor is, say, easier to change the levels of it. So instead of just completely randomizing everything, what we would do is we would randomize the order of, say, factor A. And then once we have a factor A level, we would then go to factor B and test all the different levels of factor B before returning to the next A, and then so on. So in some sense, this is, there's a couple things. The first thing is that we have replications as a random effect in this model. And in some sense, the nesting is set or chosen by the experimenter. And remember what I said before, you would have something in R that would look like AOV Y, which would be our response variable, would be something like A star B for A, B, and the interaction between A and B. And we would have an error term, an error with 2 R's term, which would look something like rep, the replications divided by, or slash, not really dividing by, it's just the slash A. and then something like that. So this would be how we would write this model in R, taking the replications to be a random effect. But the idea is that A and B, so this is, maybe I'll put a little star here because this is sort of a key thing to note, is that A and B are not physically, or I'll just say physically, nested within one another. I guess what I'm saying is that B is not nested within A and A is not nested within B. It just so happens that for whatever reason, it's hard to change the levels of A and it's easier to change the levels of B. So the classic example, like I said last time, would be you have a big plot of land and maybe B are different varieties of some plant. A is different types of, say, pesticides. Well, if you're going to be dusting a whole big plot of land, it might be very hard to carefully drop your pesticide on tiny little squares. Instead, you have to apply them to big pieces of land at once. So effectively what you would do is you would randomly assign big chunks of land to different A's, different pesticides, and then within those big chunks of land, you would have every different variety of plant B within there. So that's kind of the example, and hence why it's called a split plot design. But the point is that A and B aren't, in some physical sense, nested within each other. There's no sort of, plants aren't necessarily within the pesticide or vice versa. Now, the reason I keep trying to say that, even though it comes out strange in English, is that because you can have cases where one factor is sort of physically nested within another. So what I'm going to say is, in contrast, we sometimes have, let's say, B nested within A. Okay, so how would that work in practice? Well, let's say we want to, let's do an example, a hypothetical example. I don't have the data in front of me, but let's say we wanted to test the performance of students in high schools here. So let's say high school, let's say math performance, because everybody loves to test math abilities of high school students, right? Well, in Edmonton, in Alberta, let's say performance. Here, right, there are two, I guess there's different schools. You could have private schools, but among the public schools, there's sort of two types. There's the public school board, and then there's the Catholic school board, which run, to the best of my knowledge, sort of autonomously. I don't believe they're connected. I think they have their own control over their schools. I'm not 100% sure on that, so don't quote me on that. I actually have no idea about the finer details of how the public school system is run here. But let's hypothetically say that we have, let's say, two types of schools. Which might be, well, for lack of a better word, I guess, we'll say public and Catholic. I was going to say regular, but that doesn't sound right. We'll say public and Catholic. And maybe we also want to test the experience. We want to split the teachers into, say, two categories, those who are new and those who have a lot of experience. Because, you could imagine, well, different scenarios. Maybe the experienced teachers just really know how to teach students. They've been doing it for, set a threshold, 10 years, 20 years, whatever. On the other hand, you could argue that brand new teachers are bringing new ideas to the classroom and innovative ways to teach. So, we might not know a priori, are older teachers getting better performance from their students? Are younger teachers? Is there no difference at all? So maybe we can have something like teachers' experience And what I want to do is split it into 2 levels. So we'll say something like, let's just say less than, I don't know, 10 years or greater than 10 years. So on the surface, we could look at this and say, well, this looks like basically looks like a two-way ANOVA problem. But there is a difference, which is, so the big but is that we are not randomly assigning teachers to schools. They're already there, right? If we were to do this as some type of a proper two-way ANOVA, what we would really be doing is randomly assigning students to schools and then also randomly assigning teachers to those schools, right? To make sure that everything is fully randomized, but that's not the case. Right, so actually, the teachers are in some sense nested within the high schools. So what that means is that when we look to compare, when we look at the performance, let's say, we have to consider, we don't want to test all the young teachers against all the old teachers, because depending on which school they're in, that's going to bring in a lot of different factors, like the, well, for one, certain schools might just have more funding than others. They might have different number of students per teacher, depending on the size of, the scope of the district. So there's a lot of different factors that the school itself can bring in. So we have to consider the fact that the teachers are sort of nested within the schools. And then in that case, when we run the ANOVA, we have to consider that. And what we would want to do is test the old and young teachers within the same school and not test them in some giant aggregate sense, if that kind of makes sense. Right, so mathematically, this does change the ANOVA table a bit. Well, first, we'll say in R, what we would have, if I just go back to my A and B example, what we would actually want to write in this case is something like, oh, I hope I get this. It should be A/B if I'm A/B. And then if there's replications, we can add that in or something else. But in this case, what you're telling R is that you're testing A and you're testing B within A. They're both going to be fixed effects in this case. I guess in some sense, if you're randomly selecting schools, then you could also think of that as a whole nother testing problem. But I'm trying to keep it a little bit simpler in this hypothetical setting, right? You can actually do much more complex designs if you want to test student performance. But in any case, right, we have in the simple setting, we have two factors. We have A and we have B, which is somehow nested within A. And what does that do mathematically? Well, mathematically, that leads us to a slightly different degrees of freedom and a slightly different sum of squares. And what I should say, this notation for A/B actually tells R that what you're really doing is you're doing A, and then you're doing the interaction AB. So just for the sake of completeness, similarly, if you tell R that you want A*B, what you're really telling it is A plus B plus the interaction AB. So that's what R does. It's really the nesting notation with the slash is a shorthand notation, which tells R that you want the main effect of A and you want the interaction. You want to test B within A, but you don't want to test B on its own, if that makes sense. Right. So yeah, getting back to the idea of the ANOVA table, well, this changes things a bit. So let's say, well, first of all, we don't actually need the replications, unlike in the split plot case where we would replicate the experiment. In this case, we don't have to replicate it. I mean, we can always replicate it and get more data. That never, well, probably wouldn't hurt, except for the fact that it would take more energy. But the point is, we don't have to, much like the complete randomized block design, we don't actually have to replicate it. We'll have some degrees of freedom left over for the residuals. Not a lot, mind you, but we'll have enough. So what we'll say is, let's say A and B have Ka and Kb levels, respectively. Then what happens is, if we go to our ANOVA table, well, we're going to get a couple different things. We're going to have factor A, and then we're going to have the interaction AB. We're not going to have B on its own again. We're just going to have, and this is kind of like B within A. And then we'll have our residuals, of course. So when we look at this, we're going to get a couple things. Well, we're going to get a sum of squares, as usual. Now, the sum of squares for A is exactly what it would have been last time. Last time, what's last time mean? It would have been exactly what it would be exactly what you would have thought from a two-way ANOVA is what I mean. In this case, we would sum over, let's say, J from 1 to KB, and that term just sort of leaves the summation. But actually, I never wrote down the actual model. I should probably have written that down. Sorry. Let's write that down first, just because it'll be, I think, a little clearer. So we'll just make a little bit of room here, and then we'll write down the model, which in this case will be Yij is going to be the global mean mu plus alpha I, the ith, I guess, effect, the ith level of A. And then we're going to have an interaction term in some sense. So we could write it like the other interaction term. What I kind of want to do is write it as beta to indicate that it's B. And we'll just give it a, let's say, J with a I maybe up in the exponent here. And then we'll have our epsilon ij as always for our errors. So the point is that now we have that this is the jth level of B, but nested in A, which means that it's basically equivalent to the interaction term between A and B, but we have to remember how we interpret it in this case. It's really, what is B doing within A, some level I of A. Okay, so where are we? Well, what we're doing here, like I said, for the sum of squares, is we're just going to sum up the, well, we're going to do the sum of squares for A like we did before, which is going to just be the sum of I from 1 to Ka, and we're going to do y bar I dot minus y bar dot dot. No, that should work. Yeah, never mind. I got worried for a second that I had made a mistake in my setup. We're good. Right, so we have that, and the degrees of freedom is exactly what it was before. It's just going to be Ka minus 1. We have Ka different category means. We have one global mean. We get Ka minus 1, and then the usual mean square and F statistics will follow from below. But the sum of squares for this AB is going to be a little bit different. So in this case, what we're going to do is we're going to be doing the double sum, I from 1 to Ka, And we're going to be doing j from 1 to kb. So now what we're going to do is we're actually going to take the ijth observation, yij, but we're not going to subtract the global mean like we would say in the least, or in the total sum of squares sense. What we're going to do is we're going to subtract the ith category mean, something like this. And in this case, what we're going to get is we're going to have degrees of freedom Ka, Kb minus Ka, which is going to be Ka, Kb minus 1. Okay. Ka, yes. And then at the bottom, we'll get our residuals out. So the residuals, no, I think I do need to replicate this for it to make sense. Yeah, see, this is kind of an extemporaneous approach that I was taking to this one, but I think that, yes, we actually would need another factor or a replication for this to work. So I did make one mistake here. I had that feeling. I could just record this again, but I think that it's good to go through the thought process. So what I should have said is that there is a replication factor in here. Because otherwise, I had that worry that we were going to run out of degrees of freedom if we don't have like a replication or something in here. So I'm going to say and replicated n times, which means in green, just to emphasize the change, I'm going to have to include a subscript L there and a subscript L on the epsilons. So yeah, we need some replications or else we're not going to be able to test everything. I was confusing myself because in parallel to this video right now, I was working on a separate video where I didn't replicate, but I had a third factor, and the third factor in some sense acted in a way to give me enough data to not run out of degrees of freedom. So yeah, so that was a little confusing. But luckily we're back on track here, and what we need is we need to put an n in front of these guys just to indicate that we've in some sense summed over all of the replications. And again, I'm assuming that the same number of replications n occur for every combination of factor levels A and B for simplicity. Otherwise, things get a lot messier. Right, and then, I also need a couple more indexes here. So we need a dot there, we need another dot there, so we have 3 dots. We need a y bar ij dot and a y bar I dot dot. Okay, so we just have to add a bunch of dots in there, and now we're back on track because now we'll have enough degrees of freedom left over for the residuals, and the residuals will look like, well, the sum, in this case, I from 1 to Ka, J from 1 to Kb, and L from 1 to N. So now we're going to be summing over everything, and we're going to be summing Y, I, J, L, and we're going to be subtracting the ijth category mean with a dot there. And in this case, the degrees of freedom will be, well, I guess what's left over, right? If our total sample size, we'll say up here, the total sample size n is going to be little n Ka times Kb. So if I do the subtraction, what do we get out? Well, we get out something that should look, if I do this right, like Ka, Kb, times n minus 1. Does that look correct? Well, if I multiply it all together, yes, it should all work out, because what I did quickly in my head was note that if I summed up all of these things, what I should get is n ka kb minus 1, which looks correct. So that's always a good check to make sure that we didn't lose any degrees of freedom, right? Is to make sure that the sum of all the degrees of freedom needs to be the degrees of freedom for the total sum of squares, which is always the sample size minus 1. Right, so again, what you have here is a slightly different testing scenario from two-way ANOVA, because we're only testing B within A, and what it means is that, we need a bunch of degrees of freedom to actually test B within A. Now, more or less, I think that is all that I wanted to discuss here. As I kind of alluded to while I was, trying to find my mistake, I actually have a separate video I'm working on right now, which I'm going to upload soon. The idea in that one is to test Mentos and Coke. That is, when you put Mentos in Coke, it explodes, and I want to see, what gives you the best explosion. In that case, if you have different varieties of the same drink, like Diet Coke, regular Coke, I guess there's other ones too that I didn't consider, like Coke Zero or Coke whatever, those are all in some sense nested within the brand, because you might have Diet and regular Coke and Diet and regular Pepsi, but those are not randomly assigned. They're not independent factors, in the sense that you're not just assigning Diet to one or the other bottle. It's a specific formula that's coming from within the brand, so we have to test it within the brand factor. Similar to here, the teachers already at the school, I have to test the teachers within the school, which can make things a little bit more complicated, but gives you another idea of how to test factors properly when you're running an experiment like this. All right, so we're going to stop nested factors now, and we're going to take a break and then switch over to ANCOVA. So see you in a minute. And we are back, and now we're going to talk about the analysis of covariance, or ANCOVA, as it's often referred to. So the next section in this notes is going to be ANCOVA, which is the analysis of covariance. I guess it is covariance, but I feel like it should be analysis of covariates, because ultimately what ANCOVA is going to do is it's going to be analysis of variance. It's ANOVA with covariates. I guess it's because there would be a covariance between the factors and the covariate, compared to in the case of a properly balanced design like we talked about before, where all of the covariances would be 0 because everything's orthogonal. But side tangent, let's get back to analysis of covariance. Right, so when you're collecting data to run sort of an experiment, sometimes there are measurements that you can take about your data. So let's say, for example, you're running a medical trial. You want to see how well your blood pressure medication helps to reduce the blood pressure of various subjects. And maybe you have different blocking factors and treatment factors. Again, things like the age of the subject into two groups, say old and young. You could have the sex of the subject. You could have the amount of medication given to the subject. But you might also want to include something like a covariate, like the subject's weight, because the larger a person is, they might require a higher dose of the medication to take effect, right? So typically, maybe not typically, but in many cases, right, if you have a very small person versus a very large person, they may need different dosages of medicines or vitamins to have the same overall effect on their body, just based on their size. So the weight of a person would be a covariate, and that's something that we can't control. We can't just come in and say, okay, I need 10 people who weigh exactly 150 pounds, and I need 10 people who weigh 200 pounds, and right? You can't do that. Everyone's going to have their own weight, their height and size and things like that. But what we can do is we can measure these covariates about our subject, and we can include them in the model and take out the variation in the data that is strictly due to the covariate. So similar to blocking, what we'll be doing is trying to remove sources of variation that may be getting in the way of seeing what's actually happening with our experiment. So again, we want to test our hypothetical blood pressure medication. So what we'll do is we will try to control, in some sense, for a person's weight, for example. And what we end up with is a model that looks a lot like, linear regression with, I guess, variable intercepts. So the model is going to look something like Yij is going to be, let's say, mu plus tau I plus, and now we're going to have beta. Beta is no longer going to be a blocking factor. It's going to be a single parameter. And now we're going to have an Xij here and an epsilon ij. So what happens? Well, okay, we have the same things we always have. We have the global mean. We have the ith treatment effect. The thing that we're actually maybe interested in studying. And then what we're going to have is beta. Beta is a parameter. And Xij is going to be the ijth covariate measurement. And then, of course, this is just noise, as always. So going back to my hypothetical example, right, what we might have is we might have Y being someone's blood pressure. And in that case, it would be a function of whatever the global average is, some average of what a human's blood pressure should be, tau I, which would be the, maybe I won't write tau I. What I'll say is we'll say medicine dosage I. And then we might have some beta parameter times the weight of the subject. Again, under the hypothetical setting that if a person is larger, they might have to take more of the medication for it to have the same effect on their blood pressure. So this is the idea. And then what we do is we try to estimate beta. Beta is now a single parameter, so it will require 1 degree of freedom to estimate. And what we can do is we can compare it to the, we can basically do an f-test by comparing this model here to a simpler model. So we'll call this model 0. And model 0 is going to be the same thing, but we're not going to include the treatment effect. So this would just be saying, okay, someone's blood pressure depends on their weight based on some beta. So maybe people who are larger have higher blood pressure. I don't know that. I'm just taking a guess here, just for the sense of our hypothetical example. But what ends up happening is you end up doing an f-test. So as in linear regression, with nested models, now this is a different nesting, right? This is nested models in the sense that the model up top, which maybe I'll call model 1, so I can refer to it in some way. Model 1 has all the parameters and more that model 0 has. So that's what I mean by nested. that model 0 is in some sense a simpler version of model 1, which has more parameters in it. And when you have two linear models that are nested, well, we can do an f-test to test for the significance of those additional terms. In this case, the significance of the tau I, when it comes to actually being able to predict the values of y that come out. So as in linear regression with nested models, we can do an f-test for the tau I, in the sense, right, we're testing the hypothesis that the tau I, the null, that the tau I are all 0 or are all the same, versus the alternative that there actually is some significant difference among how the tau I affect the outcome y. Now, in this case, we don't quite get the nice setting as before, but what we can do is basically say for models 0 and 1, we get the least squares estimator. The least squares estimator, like you would in regression, your beta hat, say, but in this case, it would be beta hat and also mu hat and tau hat, specifically for model 1. So we would get our least squares estimator and compute the residual sum of squares. Sum of squares for each, which we'll denote as RSS0 and RSS1. So remember, if we're just doing linear regression, in the case of model 0, we're actually just in a linear regression setting. So we would have our x, we would have our y, we would have some data points that are just sort of floating around here. We fit a line to it, and we compute our residual sum of squares, which is just the squared sum of the differences between our data points and the fitted line. I'm kind of assuming everyone's seen linear regression before, so I'm just blazing through this. If you haven't and you have questions, please come talk to me and I can try to explain this a little bit slower. But assuming that you've already seen what simple linear regression is, simple in the sense that we just have an x and a y, a single variable x and y, then what we do is we compute our we compute the least squares estimator, we compute the residual sum of squares, and we can do that for both model 0 and model 1 with the tau I effectively are shifting the line up and down. They're changing the intercept of our linear regression model. But in this case, we're actually really interested in the tau I in the design of experiments setting. So what we do is we get an F statistic. So, well, I guess actually, first of all, we need degrees of freedom. So what I should say is we have two residual sum of squares, and they both have degrees of freedom. So in the case of the residual sum of squares for model 0, it's always going to be the total sample size minus the number of estimated parameters. In the case of model 0, we only have two parameters to estimate, mu and beta. They're both univariate parameters. In the case of model 1, well, we still have to estimate mu and beta, but we also have k different taus, but we don't exactly have k different levels. We actually have k minus 1 because there's always going to be a linear constraint, like we talked about in, I think, the first or second lecture. So actually, it's going to be k minus 1, as we often see in design of experiments. So what we end up with is something like this, minus 2 minus k minus 1. And when we kind of cram that all together, we get an n minus k minus 1 for our degrees of freedom. So now that we have these degrees of freedom, what we can do is we can get an F statistic. And our F statistic is going to look at like the difference in the residual sum of squares between model 0 and model 1. divided by the change in the degrees of freedom. In this case, it's going to be k minus 1, because we lost k minus 1 degrees of freedom when we went from model 0 to model 1. Or we added k minus 1 parameters into the model, you could say. And then what we do is we compare this to the residual sum of squares for model 1 divided by its degrees of freedom. And under our null hypothesis that all the tau i's are the same thing, this would have an F distribution with the corresponding degrees of freedom. Cool, so if you've seen linear regression, this shouldn't look too new. The point is just how it kind of fits in to design of experiments, because very often you will have covariates that you want to measure, and you can use those to help understand or better test the experimental factors that you want to test. All right. Yes, so one other model, just for fun, we can say also, well, maybe not also yet, we'll say, so model 1 effectively is simple linear regression. Simple in the sense that it's a univariate, not that it's easy. But yeah, so model 1 is effectively simple linear regression with, I'll say variable, or with intercepts depending on tau. I didn't give it an A or a B or whatever, so we'll just say on tau. So it's really like, instead of fitting one line to your data, you're actually fitting k lines to your data, one for every level of tau. But we can actually complicate this even more, and we can consider model 2, which is going to be the same thing as model 1, except I'm going to have one more additional parameter in here. I'm going to have a tau I as before, but now I'm going to have a beta plus alpha I x I j. So epsilon I j. So in this case, we're going to have beta, which is going to be the, well, I guess beta is kind of the fixed slope, but then alpha I is, this is the, we'll say the mean slope. But then the alpha I is the slope for category I. So you can complicate this slightly more, and now not only do you have, let's say, k different lines that you're fitting to your data, but they don't all have the same slope. In model 1, they'd all have the same slope. We're just sort of shifting the line up and down. In model 2, we're giving the model the ability to change the slope depending on the level I of our experimental factor. So it could shift up, it could go down, it could go the other way. And this is something that is worth taking into account, because again, going back to our hypothetical medicine example, right? Depending on the dosage, it may not affect, or I should say the dosage, if we imagine weight versus blood pressure, the slope of that line may change depending on what kind of drugs we're giving the poor person in our study. So again, it's something else that can be considered, and you can test this model. You can test covariates affecting the slope as well for your lines. All right, so yeah, that's another way we can do this. And yeah, what we'll do is I'm just going to copy over the example. So let me take one quick break, and then what we'll do is we will copy over an example. I will show you what that's all about, and then we'll talk about type 2 and type 3 ANOVA, which is has its own little confusion. And we are back with an example from the Agridat library or package in R, my favorite source for agricultural data, the only source I know for agricultural data when it comes to experimental design, but they have a ton of data sets, including one called Cochrane.beats. Thanks to our good friend, William Cochrane. Cochrane.beats data. And this is an example of data set that has a covariate in it. So you can look at this in R if you want. The actually running it in R Studio is not necessarily that interesting. There's really nothing profound about the coding, so I figured I would just copy over the results from my lecture notes, and we can just talk about them. So the Cochrane.beats data is really just going to say, well, I have a bunch of plots of land. I want to apply different fertilizers, and I want to know which ones are going to give me the best output for the beets that I have. So what we could do, if we just ignore the fact that, certain plots have more plants in them than the others, what we could do is look at this first table. So this first table is just one-way ANOVA. And what do you know? We find out that the fertilizer is very significant. So at least one of them is behaving differently than the others. But the idea is that within each of these plots, there's a different number of plants. So if one plot has more beet plants, it's probably going to give me a higher yield when I'm done with my experiment, regardless of whatever fertilizer I put on it, right? Whether the fertilizer has an effect or not, if I'm starting with more plants, I'm probably going to get a larger yield. So it makes sense to try to fit a linear model like this one here. In this case, in the red box, I now am not including my factor at all. All I'm saying is I can try to use linear regression to determine if the yield is affected by the number of plants in the plot. And sure enough, it is, right? The more plants you have, the higher your yield will be on average. So we want to include the number of plants as a covariate for our data. And what we do here is we have different ways of fitting this model in R. So we have here models 1, 2, and 3 in this table. 2 and 3. So the first one, in some sense, is actually the model 0 from above. So model 1 is just linear regression. Model 2 is going to be, I'm going to say LR for linear regression. Maybe I'll capitalize that, even though LR is often likelihood ratio, so I probably shouldn't write LR, but we'll say LR is going to be, model 2 is going to be linear regression with, intercepts dependent on the fertilizer. And then model 3 in this table is going to be linear regression with, I'll say, intercepts and slopes dependent on the FERT for the fertilizer. So these are 3 different ways, and that's the equation, right? If I use a star, a plus sign, I'm just saying I have the fertilizer. It has, I think, 7 different levels to it here, 6 degrees of freedom, so 7 levels. And then I have my number of plants, which is observed for each of my observations here. I guess there's 42 in the entire data set, or 42 observations in the entire data set. Now, Yeah, and then what we do is we can include, again, fertilizer for the intercepts to shift the line up and down. We can also include it to change the slope. And what we get is we get a collection of nested models, which can then be compared with an F-test. So when I compare model 2 to model 1, I get a p-value that's, well, I guess about 7.5%, so not that significant. Maybe there's something going on there, but it's not quite significant. So whenever I would see a p-value like that, it makes me think, well, we might want to do some more experiments to see if there's actually something going on there with the fertilizer affecting, because I mean, you kind of imagine that the fertilizer would have some effect, even when accounting for the plants. But then once we get to the next level here, we have model 3 compared to model 2, and we have a p-value that's very much not significant. So we can kind of cross out model 3 and say that we probably don't want the slopes to change with the dependent on the fertilizer. Whether or not the intercepts change with respect to the fertilizer for our model, well, it's not quite straightforward. It doesn't look like there's strong evidence. But again, it might mean that we need to do a follow-up experiment, maybe where we control the number of beats per plot a little bit better. But the key thing maybe to take away is the fact that if you forget to include the covariate, you get an extremely strong p-value up here, compared to a very not exciting p-value down there. And that's a good thing to take into account. Basically, the covariate destroyed our significance, but it might tell us that we have to try to control our covariate next time we run this experiment if we want to do a follow-up to really test those fertilizers. And just to show you that you can complicate things by adding a block factor, like you can. Remember, all of these models we're discussing are really just sort of simple building blocks. You can start to combine them with blocks and nesting and split plots and who knows, more Latin squares. I mean, they can all be combined into these sort of horrible Frankenstein-like designs. And at least in this case, right, we can include a block factor as well as a covariate. So now we have a block and a covariate. And in this case, we get absolutely really no significance for model 2 or model 3 when we do our F-tests. So again, with the block factor, and I honestly forget exactly what the block factor is, if it even tells you. Sometimes they don't even tell you in the documentation. Yeah, the block factor may not even, has kind of removed all significance now for our fertilizer. So it's looking like the fertilizer is not working at all, or there's too many other extraneous factors in here that are kind of ruining the ability for us to detect any significance. But looking at these ANOVA tables, it's good that we actually do one more thing, which is talk about the idea of type 1 and type 2 ANOVA. So that's going to be what we talk about now. So if you were reading along in my lecture notes, before I included this example, I had a warning saying the order that you type in the factors in an ANCOVA model will change the p-values that you get out in the F table. And that's something you have to be really careful about when you type in summary and you get an ANOVA table. It's something that we could kind of brush under the rug before. So this section will be ANOVA type 2 and 3, which is just horrible notation, right? Or horrible terminology. Just like type 1 and type 2 errors. Whoever remembers which one is which? I don't. And sure enough, they thought, hey, well, we like type 1 and type 2 errors so much, why don't we have type 2 and type 3 ANOVA? Yeah. But anyway, yeah, so the idea is that if we get an ANOVA table, what are the p-values testing right? It's always really good because, I mean, you get p-values everywhere in statistics, in R. You got to know exactly what's being tested or you're going to run into trouble. Now, if I just typed in summary on an AOV model like we've been doing for this course, excuse me for a second. If I were to just type in summary like we were doing for the AOV models, then I'm going to get a, I guess, type 1 ANOVA. So the default is type 1 or sequential testing. And what I mean by sequential testing is, let's say we have something like, what's the easiest way to write this down? Why don't we try YIJL is going to be mu plus, I'm going to use A, B, and C here just because I want to be able to abuse the notation. A, B, and C are going to be my factors. So if I just type this into R, then what I'm going to get is I'm going to get an ANOVA table that's going to look like A, B, C, and then there's going to be some stuff here, sums of squares, degrees of freedom, etc. And then there's going to be p-values. P-value A, p-value B, p-value C. Well, by default, what's actually happening is that each of these p-values is comparing two different models, one simpler one nested within a more complex one. What happens in the first case is we are comparing the null model, which is just YIJL is equal to mu plus epsilon, to YIJL is equal to mu plus A plus epsilon IJL. I'm just going to write epsilon just because the giant subscript is going to be assumed. So we're not actually testing B and C yet. We're just saying, okay, I can either have a model that's just a constant term mu or a constant term mu with factor A in it. Which one is better in some sense? That is, does including A in the model actually add anything to my ability to correctly predict Y? Now, when we get to the next line, we've already included A in the model. So we're going to be comparing the model mu plus AI plus epsilon to YIJL is going to be mu plus AI plus BJ plus epsilon. So now we're saying we already have a global mean mu and we have factor A. What happens when we include factor B? Do we get any better ability to predict Y? That is does the sum of squares or the error sum of squares decrease enough given the number of parameters that I'm including in the model? And lastly, we would have something like mu AI BJ plus epsilon, and we're comparing that to the full model that I wrote down above, which is AI BJ CL epsilon. Now, this might look like the order is going to matter, but the way that we set up our designs before were very special. So in most of the designs we've considered, order doesn't matter, because all factors are orthogonal. This is coming from the fact that we have balanced designs. So mathematically, if we were to consider a linear model, y is equal to x beta plus epsilon, what we're saying is that x basically has orthogonal columns to it. So x transpose x is just going to be, is that the way I want to do it? Or am I doing it backwards? No, I think that's the way I want to do it. Is just going to be a diagonal matrix. Yeah, no, of course that's the way I want to do it. Right, so mathematically what we're saying is our design matrix is orthogonal, which means that our factors testing, our factors A, B, and C in that setting can all be done independently of each other. So whether or not I include A or B or C in the model, it's not going to affect the other ones. And in which case, we don't have to worry so much about the fact that our default type 1 ANOVA is actually doing sequential testing. If instead we were doing something like multivariate regression, or we're in linear regression class and we're doing multiple regression, I guess is the word I want, then typically you would not have this orthogonality. X transpose X would not be a diagonal matrix. And that means that when you look at the ANOVA table, you have to remember that R is adding one more term in on each row of the ANOVA table and what those p-values mean. So that's why I bring this up at this point in the course, because we've just started doing ANCOVA, or added covariates in. Now these covariates are very unlikely to be orthogonal to all of the other factors in our model. It would be very surprising if they were, since they're just sort of randomly coming from our subjects. So as a result, you have to be careful which way you test the terms in your model, because the p-values may make you think, yeah, that one term looks really significant, where actually it's not. It's just because we tested them in a different order. So given all of that, yeah, what in the world are type 2 and type 3 ANOVA? So type 2 ANOVA is the, I guess, marginal ANOVA. And you can find all of this, I'll put it off to the side, in the CAR package in R, and that's under the function which I believe should be capital ANOVA. Yeah, capital A ANOVA. This is capital A, lowercase NOVA. And then you can throw in an argument and you can say like type 2 or 3 or whatever you want. So you can do these, but you can't do them in the default R. You have to load in the CAR package, which is a standard one. It has a lot of nice functions in it. So looking at the documentation, what does it tell us? It says, well, type 2 tests are calculated according to the principle of marginality, testing each term after all others, except ignoring the term's higher order relatives. So what does that mean? Well, that means, well, I'm going to make this slightly simpler. Yeah, we'll do it that way. What that means is, let's say I have a model. Let's forget about C for a second, because I don't really want to have C in there. We're going to have L just as a replicate so that we can assume that we've replicated this enough to be able to test an interaction term. So let's say I have AI, BJ, and AB, IJ, and then epsilon, IJ, L. So if I have a model like this and I do if I do a type 1 ANOVA, first I'm going to test A, then given A, I'm going to test B. then given A and B, I'm going to test the interaction term A cross B. But if we do a type 2 ANOVA, things are slightly different. We would still have our A, B, and A cross B columns, and we would have p-values, PA, PB, and P, let's say A cross B. But what we're actually testing in the type 2 ANOVA setting are slightly different hypotheses. And again, what we're going to be doing is we're going to be comparing, change to green to coincide with above. There it is. We're going to be comparing two models. I mean, in some sense, all of these F tests are just comparing two models. In the first case, we're going to be comparing the model Yij is equal to mu plus Bj plus epsilon to the model Yij is mu plus Ai plus Bj plus epsilon. So compared to what we had above, remember above we tested A without anything else in the model. We said, okay, we can either have a model that's all by its with just mu, or we can have A and mu. Whereas in this case, when you do type 2, you take all the other factors and you shove them into the model, except for A and any interaction terms involving A. So that's why I don't have A cross B in here. Similarly, and kind of symmetrically, if I were to test this next row, what I'm doing is I'm considering the model with AI already in it, and then compared it to the model with both AI and BJ inside the model. Now, lastly, if I were to test this interaction term, I would be testing the model with just the AI and BJ, the main effects or the main terms, and then I would compare that to the full model, which is all the terms, including the interaction term, of course. Ij plus epsilon. All right. So that's what type 2 ANOVA is doing. And if I had let's say if I really wanted to, I could include, let's say, a C in here. And if I had a C, then I would be adding C on to everything, because C does not interact with, C is, first of all, I'd want to include all the factors that are not higher order interactions of any of the ones that I'm testing. So in this case, I would just have C sort of plugged in everywhere. And when I ran the test, if I were to run this test with C, I don't have the right indices now. I still just have IJ, which I forgot to even put L in there, but it doesn't really matter for the sake of this hypothetical example. In this case, I'd be testing AI, BJ, and the interaction term AI or AB, IJ, compared to the model that includes everything in it, which would be the mu, the A, the B, the AB term, and the C term. So again, this can be a little confusing when you first see it, but it's not as bad as it looks. And the nice thing about this is that it is basically the order doesn't matter, which is nice because it means that however you type your equation into R or whatever stats package you're using, you're still going to get the same p-values out every time. When you're in the type 1 ANOVA case, if you change your equation just by reordering the terms, you might get different p-values out, and that can be really confusing and also misleading if you are not aware of that or if you see that in practice. So it's a really important thing to be aware of. And now that leads us to type 3 ANOVA. I'm going to take a quick break and then we'll talk about that. And we're back, and we're going to fight our way through one more ANOVA table before we're done with this lecture. And what we're going to do is look at type 3 ANOVA. Again, worst possible terminology ever. It's almost like somebody's doing it as a joke. Anyway, if we look at the documentation in the R function, ANOVA, then it says that type 3 tests violate marginality by testing each term in the model after all others, including the higher order interactions. So it's going to look a lot like what I just wrote, but I am going to write it all out just for the sake of completeness, because I want to make sure this is clear, because it is going to be important when you're actually running experiments with real data. If you don't have a nice balanced design, or if you have a balanced design, but you also have covariates in the model. So going back up to this table, it's going to look similar with one big difference. So when we consider the null model here, we're going to still have mu. We're going to have the bj term, but we're also going to have the interaction term abij. And then we're going to compare that to the full model, which is the one with, I'm going to ignore the c here, with all the three terms, a, b, and a, b. So what we're doing now is we're doing the exact same thing we did above, but we're including that higher order interaction term that depends on A. And similarly, you can kind of guess where this is going, but just for the sake of completeness, I will write it all out. We have AI plus the interaction term, which is still here, ij, epsilon. And we have the full model, A, B, I, J, epsilon, I, J. I guess there's supposed to be an L in there. And then for the last line, it turns out that the last p-value, that is the p-value for this interaction term in my simple two-factor, let's say two-way ANOVA experiment, is actually going to be exactly the same as it was in type 2 ANOVA above. Because all we're going to do is we're going to remove the interaction term from the model, and we're going to consider two models, the one with the interaction term and the one without, or the way I'm writing it, the one without first versus the one with second. So we have an AI, BJ, A, B, I, J. So if you notice, for example, all of these three models on the right-hand side are all exactly the same thing. And it also turns out that this p-value here is going to be the same as the p-value in the type 2 case. If there were higher order interactions like an ABC term, that would not be the case, because in type 2, we would not include the higher order interactions while testing a lower order term. Whereas in type 3, we just include everything. Okay, so why would we choose one over the other? Honestly, I don't have a good explanation for that. What the most important thing to remember is, what are you actually testing? I mean, if you might want to do type 1 ANOVA. I did that in the example earlier in the course, right? Up here, I was just doing type 1 ANOVA because I'm saying, okay, if I already include my covariate and maybe a block factor in the model, what happens if I now include the fertilizer term? I don't really care about the reverse in this hypothetical example, because I just want to test that fertilizer factor sort of conditioned on the fact that those other terms are already in the model. So type 1 ANOVA, as it defaults to, may be the thing that you want to do. But there are cases where you might want type 2 ANOVA, or you might want type 3 ANOVA, and it's always good to just know what hypotheses you're testing, because that's really important. If you come with a significant p-value and say, I found a significant p-value, this is good, we have something, then the question is, well, what in the world does that significant p-value mean, right? It has to have a meaning. It has to have a hypothesis test, which is going to tell us what we're rejecting, what null we're rejecting in favor of what alternative, and what does that actually mean for the data and the, I guess, write-up afterwards if you're actually trying to write a report for some client or customer or journal or whatever. So yeah, this was kind of, again, the grab bag lecture. I think we're basically done now for today. What did we do? Well, we went through this entire second chapter in my notes. It was all about multi-factor experiments. So we did everything from blocking to two-way ANOVA. We talked about nesting and split plots and Latin squares and covariates. And now type 2 and type 3 ANOVA and different ways to analyze this data once it's been collected and on your computer. Moving forward, the next thing we're going to do is take a quick sort of left turn and enter a whole new section that's going to be somewhat orthogonal to the rest of everything we're doing in this course. Rather than looking at new designs, what we're going to do is we're going to talk about multiple testing, because whenever we have tables like this, we have a lot of p-values. And when we have a lot of p-values, we have to correct for multiple testing, or we could get ourselves into trouble with too many false positives. And it's another way you can be in trouble doing statistics. So in the next lecture, we will pick up with that starting, I guess, next week. So I will see you in that lecture.